Hello and welcome to this presentation from Micro-Epsilon. Today I'll be introducing you to one of our most popular product technologies, that of eddy current displacement sensors. My name is Wedgbrow and I am the Business Development Manager for Micro-Epsilon here in the UK. In today's presentation I'll be introducing eddy current displacement sensors, where I'll be covering the measuring principle, the key factors you need to know when using them, and the typical applications where the technology has been used. So, let's begin with the eddy current measuring principle. Inside the sensor is a coil which is fed with an alternating current at high frequency, which causes a magnetic field to be generated. If there is a magnetically conductive material, i.e. metal, within the magnetic field, eddy currents are generated which form another field. This field counteracts the field of the coil, which causes a change in the coil impedance. The impedance can be presented as a measuring value on the controller. The controller, cable and sensor are a complete calibrated channel. The electrical characteristics of each component combined are used to determine the resonant frequency which is needed to create the magnetic field and induce the eddy currents into the target. The most important advantages of eddy current technology are they only measure against metal targets, and we can measure against ferrous and non-ferrous materials. They can measure in hostile environments. Dirt, dust, oil are not affecting the measurement. Small sensor designs allow for use in high pressure environments up to 2000 bar and temperatures up to 200 degrees C. They offer very stable, robust measurements. We've been selling eddy current sensors for over 40 years, and we have a wide range of sensors and customized solutions available. Our sub-miniature sensors offer solutions to installations in the smallest of spaces. The high carrier frequencies allow for fast response in dynamic applications. We talk about the sensors being able to measure in all sorts of environments. So I created a little video as an illustration of the possibilities. Pay attention to the reading. Sand or dirt have no impact on the measured value. The eagle-eyed may see a flicker of movement, but it's actually due to the metal spoon used to dispense the sand being too close to the sensor. Even oil has no discernible effect. The 1 micron change seen in the reading when the sensor is fully submerged is due to the fact that the capacitance of the magnetic field is changed slightly and gives the smallest of offsets. If the sensor is not fully immersed, then oil on the target surface is not seen and the reading is exactly the same as before. We have two basic sensor configurations. Shielded sensors are categorized by the fact that the metal casing of the sensor body extends along the whole length of the sensor. An unshielded sensor is one that has the front peak cap exposed. The target surface area should be 1.5 times the sensor diameter for shielded sensors and 3 times the sensor diameter for unshielded versions. If you're looking to use an unshielded sensor, then you must take consideration of how the sensor is mounted. A sensor mounted proud is the standard method and requires no further adjustment. Remember that the field lines spread wider from the coil on the unshielded type. Mounting an unshielded sensor flush in metal will restrict the magnetic field lines and thus reduce the range and performance of the sensor. If your installation requires a flush mount, then we would need to make a factory calibration of the installation condition to ensure you get the best performance. Mounting an unshielded sensor flush in a recess is also possible, provided the surrounding area is non-metallic and at least 3 times the diameter of the sensor. Otherwise, perform an in-field calibration if possible. For shielded sensors, as the name suggested, you are able to flush mount in metal. The factory calibration takes into account the nut position. Therefore, in a totally flush mount arrangement, we would recommend an in-field calibration for optimized measurement performance. There will be requirements to mount multiple sensors together in close proximity. We have seen that the sensor produces field lines which form the eddy current in the metallic target surface. When we introduce a second sensor, we have to consider the influence of the field lines on each other. Maintaining a distance of either 3 times or 1.5 times the sensor diameter between sensors avoids crosstalk or interference. If the sensors are closer than this distance, then we must separate the carrier frequencies or synchronize the sensors to avoid crosstalk. Please check with us which models are able to use separate frequencies and which need synchronization. With our range of eddy current sensors, we offer measurements from 80 mm down to 0.4 mm. It should be noted that the bigger the measurement range, the larger the sensor will become. In order to measure accurately on a metal target, there are a number of conditions that should be met. For unshielded sensors, the target area should be 4 times the sensor diameter, and for shielded sensors, 2 times the sensor diameter. This is not to say that smaller targets cannot be measured. They can, but range and performance may be compromised, and therefore additional calibration may be needed either at the factory or in field, depending on the sensor controller used. The second consideration is that of material thickness. We are inducing eddy currents into the metallic surface. We therefore need a certain thickness of material in order for the eddy currents to form and be stable. For accurate measurement, you should aim for your material to have 3 times the penetration depth. The type of metallic material will influence the required thickness. The carrier frequency used in our systems is typically 250 kHz up to 1 MHz, depending on the measurement range of the sensor. We also need to take care of the magnetic properties of the material. The amount of iron in a material will influence how the eddy currents form in the target. The behavior is very different between a ferrous and non-ferrous material, and therefore we need a different calibration set for ferrous materials than that for non-ferrous. Our standard factory targets are either ST37 steel for ferrous calibrations or aluminium for non-ferrous calibrations. A quick and easy way to deduce the material group is to use a magnet. If it's attracted, then it's ferrous. The wide area of the measuring spot makes small tilt errors in the surface negligible to the measurement performance. The sensor is essentially averaging the result of the tilt. Even targets with greater tilts can still be measured. As the tilt angle becomes greater, the fields generating the target at the furthest point become less, and therefore tilted targets greater than 6 degrees should be factory calibrated. Measuring on cylindrical targets is also a common task for eddy current sensors. The recommended diameter sensor ratio is 10 times. In many cases, the customer is simply looking to measure changes in rotation, such as runout. This does not necessarily require an absolute measurement to be made, but for those scenarios where it is required, we are able to perform in-field calibrations. In addition, calibrations can also be made for targets that are smaller than the recommendations. Over the last few slides, I have gone through various criteria around mounting the sensors and the required target geometry. They are the ideal scenarios. The reality, however, is that most installations are likely to be non-standard. So how can we meet or exceed the specifications in those situations? When we do a factory calibration, we calibrate against standard targets and store a range of values in the controller across the measurement range. If the installation differs from our setup, then some deviation can be expected from the ideal measurement. When using our DT3060 or 3070 controllers or our 3300 controllers, customers have the inbuilt option for field calibration. This allows them to make their own final characterization or linearization of 2, 3 or 5 points over the measurement range to tune the system to your own unique requirements. So to illustrate the field calibration, I've mounted the sensor in a micrometer fixture. The first thing I will do is select the factory calibration for ferrous material. As I adjust the target position with the micrometer, you can see that the sensor is reading through the measurement range, but with some deviation to that seen on the micrometer display. This is because the installation location and target shape is not matching the factory default. By performing a field calibration, I can teach the sensor the boundaries for this installation and tune the sensor to measure more accurately. I have a 2mm sensor connected to the DT3061 controller, and in this example I'm doing a 3-point linearization. All our sensors have a 10% offset from the front face of the sensor, so the effective measurement range for this 2mm sensor is 0.2 to 2.2 millimeters as read on the micrometer. I am then simply adjusting and recording the position as per the controller instructions. In the good old days, I used to have customers take more than half a day to perform linearization of an eddy current system. With the right setup, this can literally take minutes to complete. So once linearized, I can now move the target back to the start of the range and then move through the full range of the sensor. You should now see how close the readings match. Simple and effective. All of the Micro-Epsilon sensors and controllers are actively temperature compensated, sensors up to a maximum of 180 degrees C and controllers up to a maximum of 50 degrees C. This means that the temperatures of the sensor and the controller are recorded during operation and considered in the measurement result. Consequently, you get an extremely stable measurement signal. The temperature curve above compares a Micro-Epsilon sensor, the green line, with a competitive product, the red line. The overall temperature compensation range is dependent on the model type selected. So in this video, I'm aiming to demonstrate the stability of the eddy current sensor in harsh environments. Please note this is not a controlled environment, it's my kitchen. The sensor is mounted in the micrometer fixture measuring to the base of the saucepan. I'm pouring cooking oil into the pan and then turning on the gas. The thermal image gives you an indication of the oil temperature, whilst I've also highlighted the sensor reading as the green box and also the sensor temperature, which is the red box. Being mounted in a metal block, there is some lag between the sensor temperature and the oil, but you can see the stability of reading despite the rapid increase in temperature. Indeed, the main variations we see are caused by bubbling oil around the housing, lifting the sensor slightly. This whole video is about 9 minutes long, so I have skipped ahead with the sensor's temperature well above 100 degrees C. Once I turn off the gas, the effect of the direct heat under the pan is immediately reflected in the contraction of the target, which you can see how the pan and the value relaxes back to the original sensor value. Deep fried eddy sensor, anyone? So remember that a controller, cable and sensor are a complete calibrated channel, but the form that this takes will be dependent on the model you are using. We offer 4 basic configurations in the Eddy Current portfolio, which I will highlight now. The DT3001 is a self-contained device, essentially plug and play. You select the measurement range and material group, ferrous or non-ferrous, and away you go. Perfect for standard installation applications. The DT3005 series separates the controller from the sensor head, reducing the sensor head size for easier installation. The 3005 heads and controller are sealed for up to 10 bar, and special calibrations are possible in our factory for your target material, but no further adjustments can be made after. The DT3060 and DT3070 series represent our latest controller technology, featuring Ethernet connections and the in-field linearization as you have seen earlier. Sensors are sealed for ingress front and back and are pressure proof. Check specifications for the individual sensors. Controllers can be calibrated for multiple characteristics so that you can have a sensor calibrated for both ferrous and non-ferrous materials. It features temperature output and limit switches for process control. Our final controller is the DT3300 series with inbuilt display. Sensors are calibrated to a unique board inside the controller, which can be exchanged to allow for multiple characteristics and cable length changes. This is our fastest controller with frequency response up to 100 kHz for sensor ranges of less than 1 mm. And 25 kHz for all others. It too has limit switches for process control applications. Our Eddy Current sensors use an air coil. That means they have no ferrite core, which is typical of an analog proximity sensor or inductive sensor. The use of an air coil gives significant advantages in terms of the fact we can calibrate eddy current sensors for both ferrous and non-ferrous materials. The high carrier frequency used allows for very fast response times, and our calibration process gives exceptional measurement performance. In addition, the high carrier frequency also means that the eddy current sensor is unaffected by magnetic fields. There is no ferrite core to demagnetize. So let's now take a look at some of the applications where eddy current sensors are used. In reality, there are thousands of installations, so I've selected some of the more common tasks for your appreciation. Within the wind turbine are mounted numerous sensors from Micro-Epsilon. They're utilised to perform condition monitoring tasks and avoid unnecessary maintenance visits. Most turbines are located offshore, so it takes time and money to check each individual installation. Feedback from our sensors ensures optimum performance and warns of potential issues due to wear or fatigue before they become problems. Monitoring the radial and tangential displacement of the clutch ensures smooth delivery of energy from the rotation of the turbine. High winds can lead to unacceptable oscillations in the structure. Monitoring the movement of the nacelle to the tower ensures that the structure remains sound. Monitoring the bearing gap between the bearing surface and the drive shaft is one of the primary uses of an eddy current sensor. An oil film in the lubricating gap prevents direct contact between the bearing surface and the shaft. Improved sliding properties of the bearing increase the turbine's effectiveness while prolonging its service life. Measuring shaft movement and expansion is one of the most common applications for eddy current sensors. Whether you're looking to measure radial growth, runout, oscillation or axial expansion, eddy current sensors have been used for many years in these applications. The combination of small sensor size and fast response times provides invaluable data to customers in the development of their machines and products. Examples here of eddy current sensors used to measure the turboshaft oscillation on a turbocharger, where two sensors are mounted to look at movement in both planes simultaneously. Imagine a scenario where you have a perfectly rotating target with constant gap. If that target material is non-ferrous, then an eddy current sensor will measure the gap perfectly as the shaft rotates. Now consider a ferromagnetic metal like iron, nickel, cobalt or alloys. These can have areas in the material with different magnetizations called Weiss domains. These in turn dampen the sensor's eddy current field differently. Even with constant distance between sensor and target, different distance values can occur as the target rotates. The domains can be reproduced but show unrealistic radial runout deviations within one revolution. Experience has shown that these are between 5 and 15 micron, but can be up to 40 micron in the worst case. However, as they are repeatable, it is possible to post-analyze the data to observe the true shaft behavior. Our ability to build sub-miniature sensors has opened up possibilities for customers to perform measurements that simply were not possible before. Our smallest sensors are literally 2 mm in diameter. We have many examples of eddy current sensors used in the development of engines, including looking at secondary piston movement and cylinder head breathing. The small shape and size of the sensors enables them to be mounted even on moving parts and in fired engines. Another extreme environment is to obtain a homogeneous oxide-free aluminium die-cast. The aluminium level in the open mould must be kept constant to within 1 mm. A constant level is achieved by controlling tilting of the furnace. The current level is measured and monitored from above with air-cooled eddy current sensors. A temperature stable output signal and the high operating temperature of the eddy current sensors are particularly significant in this measurement. A similar principle is used for solder wave height control in the electronics industry. In the production of aluminium die-cast parts, liquid aluminium is pressed into a mould under high pressure. The two mould halves are held together with significant force. Despite this high contact force, the tool halves are pressed apart minimally. This process is also called mould breathing. Minimal openings are normal and intended during this process, but if the gap is too large, this causes fraying on the component. These splinters need to be reworked to meet the high quality standards of the final product. If aluminium residues remain on the tool, they also lead to increased wear, which reduces tool life. Monitoring tool deformation using inductive sensors based on eddy currents enables high product quality combined with improved tool life and reduced rework. Usually 3 or 4 Eddy Current DT3005 sensors are used to ensure consistent gap monitoring. The application of zinc to metals ensures longevity and reduces the chance for the material to oxidize. The coating process and thickness relies on the position of the base material as it passes through the bath and is controlled by a series of actuators. The strip position is monitored by a series of 40 mm range eddy current sensors spread across the material width, each providing positional feedback to the system to control the actuators guiding the strip. Sprayed skins for vehicle instruments and controls and for airbag cladding are sprayed in a heated mould using a robot-guided nozzle. Here, tight tolerances are required, particularly with the airbag as a safety critical part. For this reason, the thickness of the sprayed skin must be inspected during the spraying process. An eddy current sensor in combination with one of our laser triangulation sensors is used here. The eddy current sensor measures the distance to the nickel-coated spray mould, distance A, and has an opening in the center through which the laser sensor measures the distance to the sprayed part, distance B. Remember, the eddy current is only interested in metallic targets and sees straight through the sprayed coating. The use of the air coil in our eddy current sensors makes this combination possible, as the laser sensor can look through the eddy current sensor at the same measuring point. When both signals are subtracted, the thickness of the applied sprayed skin is measured, which is marked as C. The quality of textiles depends on the uniform thickness of the yarn used. Any thickness variations are directly visible in the material. These thickness variations are measured in draw frame machines and compensated by closed-loop controlled stretching equipment. At the input of the draw frame, the thickness variations are transferred via probe rollers to an eddy current displacement sensor. Remember, the sensor can only work on metals, so a direct measurement of the yarn would not be possible. The derived thickness from the roller position is used as the basis for the control circuit in the following stretching equipment. A second sensor repeats the measurement as a check at the end of the process for quality monitoring and documentation. These machines are extremely fast in operation, so the dynamic response of the eddy current sensor is key to this measurement. In addition, the presence of large amounts of dust created by the textile fibre has no influence on the sensor's performance. Another application that utilises eddy current sensors is that of turbo speed measurement. The spin-up of the turbo is essential to reducing the lag between when you apply the accelerator and the expected power kick the turbo delivers. Eddy current sensors are mounted directly in the compressor housing of the turbo and give pulse feedback from the fins or blades of the turbo as they pass. The fast response is key to this measurement, with multiple blades passing every rotation. The system is capable of measuring speeds up to 400,000 RPM. Fluctuations of temperature lead to thermal expansion and extension in machining processes, and therefore can cause significant problems when holding tight tolerances in a milling process. A highly precise non-contact displacement sensor from Micro-Epsilon measures this shift of the spindle. With the information from the sensor, the CNC control unit can do an active compensation of the axial extension. This direct feedback of the expansion greatly improves the accuracy of the milling process rather than just relying on a reading of material temperature. Eddy current sensors from Micro-Epsilon have even found themselves on aeroplanes. Flight qualified, they are used to check flaps, landing gear and door controls with up to 70 sensors fitted on a plane. Despite the age of the technology, the development for eddy current sensors continues. The ability to embed the coils in ceramics through one of our group companies opens up further opportunities for design and encapsulation. Indeed, it is this ECT technology that enables us to open up new customization and OEM design. As an example, the European Southern Observatory, based in Garching, Germany, relies on high precision displacement measurement from Micro-Epsilon for a project to build the world's largest mirror telescope in Chile. The eddy current sensor systems used for displacement measurement are the most precise ever used in a telescope. They determine the position of each single mirror segment in 3 axes to nanometer accuracy, with over 5,000 sensors being used. We're coming to the end of the presentation, so let me now summarize what we have learned. Eddy current sensors are able to measure distance, position movement and vibration, even speed against metallic targets. Our sensors are developed to withstand both normal and harsh industrial environments. The eddy current principle allows us to create precise measurements that are stable with temperature, and they afford us the ability to make dynamic measuring systems. We are able to make customized solutions with over 400 sensor variants to select, and they help us to solve a wide range of applications. If you want to keep up to date with all things Micro-Epsilon, then make sure you're following us on LinkedIn, and also make sure you subscribe to our UK newsletter for product news and information about the next events. If you require further information or have any questions relating to the content of this presentation, then please send us an email and we will be sure to get back to you. Thank you for watching. Goodbye.